This is Magnetism Section 2. It's number 16 through number 30. And this first one, we're just talking about making an electromagnet. So if I want to make an electromagnet, that is a magnet that uses electricity to generate the magnetism, I need a battery, some wire, and I need a nail. And the nail actually here is really optional. You don't have to have the nail. It kind of helps to have the nail, but you really don't need to. Um, it helps because you can wrap the wire around the nail itself, and that makes it a coil, and when you run current through it, that produces electricity. For number 17, a galvanometer. This is a device that we call it analog because there's no digital numbers here. There's no red numbers that you would typically see. But this galvanometer basically uses a coil that's wrapped on the inside, and I can measure both current in amps, or I can measure potential difference in volts. So that's what we can use it for. We can do either thing. These are the little places where you would put your wires in order to hook it up, similar to the multimeter that we used in electricity, but different in the kind of how it's constructed. Number 18, loops of wire in a motor rotate because you have a magnetic field that exerts force on the moving electrons in the loop. So we're going to actually build a little motor, but you have the, not a mower, but a motor. We will hook up some current into this wire, and then you're going to have some wire here that's insulated, and then we strip it. We take all the plastic off the ends, and it will actually, if you kind of bump it a little bit, it'll spin in a circle. This is a more complex motor. Looks like it came out of some sort of machine, and we can take one apart and kind of look at it too. Number 19, the magnetic pole in the northern hemisphere is actually located in Canada. It's not at the actual North Pole. It's actually just a little bit south of there in Canada. So that's where the magnetic pole in the northern hemisphere is located. Earth's magnetic field is most likely due to convection currents in the molten part of the Earth's interior. So the inside of the Earth is liquid, and as the outside of the Earth rotates, this also rotates too, but when it rotates, it doesn't rotate real smoothly, and so we think that's where the electric field comes from. You have to remember that a lot of this is molten iron. It's got an iron core on the inside, and remember, iron is magnetic. So if you're moving those little liquid iron atoms around, you end up with a pretty good magnetic field. Number 21, the discrepancy between the orientation of a compass and true north is known as, we call that magnetic declination. So if I look, this would be the north geographic pole. So this is where Santa Claus would live. So I'm going to put SC there. This is wrong. This is actually the south. It is the south, S-O-U-T-H, magnetic pole. And this is the north magnetic pole of the Earth. So we live somewhere about right here. Canada would be about here. South America would be down here, so we'll actually put as South America. This is North America. And the south pole of the magnet is actually at the top of the Earth. That is where the north geographic pole is. And if you think about it, it makes sense because a compass always points north. So if I want the north end of a compass to point north geographic, it's got to be north on the compass to actually point to the south end of the magnet inside the Earth. But the angle between the two, so between here and here, this angle is called magnetic declination. And that's really what this question is about. For number 22, it says the force on an electron moving in a magnetic field will always be largest when its direction is perpendicular to the field. So if I have a magnetic field that is pointing in this direction, and usually we use the letter B, if I want a particle, for example, maybe a proton, to be affected by it, I don't want that proton moving left or right. I want it moving straight across. I guess you could think of, there's an old game named Frogger, and the cars would go left to right. And if the little frog ran with the cars, it wouldn't be a big deal. But the goal of the game is to get the little frog to go across the traffic. You can think about if you roll a ball out in the street in the middle of a really busy highway, that will affect the ball. The ball will get kicked to that direction. So that's why we see the force being the biggest when it's perpendicular to the magnetic field. For number 23, the intensity of cosmic rays bombarding the Earth's surface is really the largest at the poles. And so if I have a magnetic field, a cosmic ray coming in, if it has to pass through all these magnetic field lines, it tends to get distorted and will usually be really weak when it hits the Earth. But if they're coming from the poles, notice that there's no magnetic field lines there. I know we're getting a lot of extra stuff here. There's no magnetic field lines to really block them, so you get bombarded by that. You also get bombarded by solar radiation and all kinds of other things at the poles. Not a very good place to live for a long period of time. Which of the Earth's geographic poles is nearest the magnetic North Pole? So the magnetic North Pole, remember this picture is actually wrong. We're going to get rid of what you see here where it says South Magnetic Pole. This is actually the North Magnetic Pole. I don't know why this picture is so bad, but it is. But it proves a point that most people assume that's where the magnet is on the Earth, is this would be the North because that's North Geographic, and it's not. This is the South Pole of the Earth, the South Magnetic Pole, and that is located at the North Geographic Pole. We talked about it earlier. If I have a compass, that compass points towards the North Geographic, which is really the South Pole of the magnet inside the Earth. Just a really weird concept, something that you probably didn't know. Which pole of a compass needle points towards the South Pole of a magnet? We already said that. It'd be the North Pole. So once again, if we put a compass right here, the compass would say that I'm going north because I want to go North Geographic. And once again, we got to get rid of these guys because they're not right. We can change them south here, but my pen doesn't work real well, and then north on this side. For number 26, if a compass is moved from the northern hemisphere, so from up here to the southern hemisphere, the magnetic needle will not change at all. It will still point north. You kind of see that in that one. I'll bring it back here. And once again, we're going to fix our little picture here. Make that south, make that north. It's north magnetic, south magnetic, and the red indicates that that is pointing towards the north. So this would be the north pole of the magnet. It's got to be attracted to the south pole of the Earth. Really weird, I get it, but that is the way it works. It's not wrong. Number 27, magnetic field lines surrounding a magnet are conventionally drawn from north to south. So they actually go from the north pole of the magnet to the south pole of the magnet. You see that in this diagram. For number 28, which force field can increase a moving electron speed? So we talked about two fields. The electric field will make the electron speed bigger. Remember, we said that the magnetic field, if you remember, the magnetic field won't make it go faster. Instead, the magnetic field will change the direction. So we'll just write changes the direction. So electric field will change speed. Magnetic field will change the direction of the electron. Oops. So I'm going to go on to the next one here. Which force can accelerate an electron but never change its speed? It's a magnetic field. And remember, we have to define acceleration. Acceleration is the change in velocity, and velocity is speed in a direction. So if I change the direction, leave the speed the same, it actually is accelerating. But the magnetic field will change the direction but will not change the speed, and hence why you see it accelerates, because that is a change in velocity. Finally, the last one, number 30 that we'll do on this video, is changing the magnetic field intensity in a closed loop of wires induces what we call both current and voltage. So if I have a magnet, okay, so I'm going to put a magnet here and one here, and then I take a closed loop of wire. If I change this magnetic field that's passing through the wire, I actually can make it a battery. Kind of like a battery, but it would have current flowing through it, and it would have a potential. This is what we typically will call, you could make something called a generator, G-E-N-E-R-A-T-O-R. It's just the opposite of a motor. and that is number 1 through number 30.